Bismillah ar-Rahman ar-Rahim. Peace and blessings upon you all. Dear students, we have actually converted in our previous lectures from RE to the NFA using Thompson's construction. Then we did NFA to DFA using subset construction. And now today we are here. That is from DFA, we're going to have a minimized DFA. Why we do so? Because the NFA, if NFA has an n states, the DFA can have 2 raised power n states. That's a huge thing. Okay, so we would like to minimize it for many reasons. Okay, because this DFA size will determine 3 things. One is the space. Okay, I don't know what's happening with this pen. This is space. Then we have a time and also the efficiency. Okay, larger DFA will take up more space, will take up more time, and will be less efficient. So if we have lesser states, it will take up lesser space, it will be faster, and it will be efficient. Okay, so we got to minimize it, but we should not do something that if we had a DFA here which represents a particular language, and then minimized DFA should also represent that language. Okay, so it should not cut out anything. It should actually be equivalent. So whatever I do here should be equivalent. Only thing is I would like to remove something which is not used, okay, which is something redundant, which is something extra. So what are those things? We'll discuss them. Basically there are 3 things which we need to take care of. One is the unreachable state, another is a dead state, and third thing is equivalent states. Okay, so what are these unreachable states, dead states, and equivalent states? I will try to first give an example and then come back to this. Now if you look at this example and you see something like Q6. Okay, now Q6, if you see, the arrow goes from here. Okay, 1 second. Okay, now arrow goes from Q6 to Q4. But is there any way that we go from a start state to the Q6? Because we go from Q0 to Q2, then we go to Q4, then we go to Q5 and Q3. But there is no way that we can reach from the start state to this Q6 states. So this is simply unreachable state. That is the state which can't be reached. So this is what we say here. If you are having a string W and you want to go from whatever, from Q0, from start state, and you reach to that state, is not true. If it is not true, that means it's unreachable state. Okay, so that means you can't reach to that state simply. So we can simply remove this. So this is of no use to us, because if you can't reach to this state, so it will be no use for recognition of our tokens, because we are trying to recognize our tokens. Okay, from the character string. When this state is not reached, so it's of no use, right? Now what about the Q3? Now if you see Q3, you from Q2, if it is 1, you go to the Q3, and after that if it is 0 or 1, you stay on that state. From Q1, if you have 1, you go to Q3, or Q5, you have 1, you go to Q3. But Q3 will lead you to nothing, because when you're on Q3, it is non-accepting state. If you are in this state and you take 0 and 1, but you still stay in this state, so that this is simply a dead state. Okay, this is a dead state, because this leads to you nowhere. Because it doesn't lead to your because we know we need to have an accepting state at the end, so as to accept our whatever input string we have. If you are on a Q3 state, it will lead you nowhere, so it's again of no use to us. So we say we can remove this dead states. So Q6 and Q3, unreachable and dead states, we first remove them. Okay, how we remove them we will talk about later. And now then there are some states which are equivalent. Okay, now if you look at the Q0 and Q4, so what's happening on Q0 and Q4? Just have a look that Q0 on 0 goes to Q2, and Q4 on 0 also goes to Q2. So that means they are equivalent, because they have the same behavior, the same characteristics. So we can merge Q0 and Q4 together. Okay, and same is with the Q1 and Q5. because when the q1 and q0 and q4 are merged together and they both go on 0 to the q2, okay, and here q1 and q5, then we'll, on q0 1 goes to q1 and q4 1 goes to q5, and from q1 0 goes to q0 and q5 0 goes to q4. So if we combine these two guys can also be combined, so they are also equivalent because the characteristic is same, right? So we can have a minimized DFA. So we have here minimized this DFA. If you could see, this is q0 and q4 combined, this is q5 and q1 combined, okay. So these two guys are combined, these two guys are combined. So this is how we minimize, okay. Now we need some formal algorithms to minimize the DFAs, and we'll discuss them. And we also need to elaborate on the equivalence of these states. We need to talk about what's called as distinguishable and indistinguishable states. Now those equivalent states are actually called as indistinguishable states. So they will be indistinguishable if they lead to a same state R, okay, which belongs to the Q, the set of states we have, definitely. So if from P on taking a string W, you go to the particular state R, and if you do same string on state from state Q and you still reach to the R, we say they are indistinguishable, right? And we may have different algorithms work differently, okay. So we may also say that the states are indistinguishable if they are symmetric, okay. I mean, if they are equivalent, and in equivalent means we need to have that firstly it should be reflexive. If two states are reflexive, if P is not Q implies to Q is to P, that means they are symmetric. So there is a symmetry, and also it can be transitive. It has to be transitive. So Q, and if Q is similar to R, so which implies to P is similar to R. So this is what's called transitivity. If all of these things hold, we say they are equivalent. When they are equivalent, we say they are indistinguishable, okay. Now this indistinguishability is important to merge the states, right? So we have now many algorithms which will work to minimize the DFA, right? So we need to have two observations. First is removing unreachable states. It may also include the dead state. And second thing is merge equivalent states, right? So two things we got to do. So equivalent states are actually which are indistinguishable, so we can merge them together, and unreachable or dead states got to be removed. So how we remove unreachable states and all, we can do that in the breadth first search or depth first search, okay. We go to the state, and if we can't reach to that particular state, we say it's unreachable, and we can remove that simply. Then how we minimize later on, that means how we merge equivalent states, is we use many algorithms. One of them is by the E.F. Moore, which we discuss in this lecture, is the table filling algorithm. Then there are other algorithms like Hopcroft and Brzozowiecki algorithm, and there's also one more thing which is called as Myhill-Nerode term. We minimize using a Myhill-Nerode term. That's also possible. We have Myhill-Nerode term. We can minimize our DFA using Myhill-Nerode term as well, right? So broadly speaking, we got three guys. One is the Edward Moore's algorithm. We got Moore's algo. We got then the Hopcroft algorithm, right? And third thing we have is Brzozowiecki algorithm, okay. Now this Edward Moore stuff, this was done in 1956, okay, and this aims to find pairs of distinguishable states. This is what we will discuss in our this thing in this lecture. And the Hopcroft, on the other hand, okay, it tries to, it computes the minimal automata by refining the partition. It does what? It refines the partition. It creates a partition. It refines a partition. This guy first creates two partitions. One is the final state, and then other partition is the non-final states, and then it starts refining till it gets the minimal DFA. Okay. And in the Brzezinski's algorithm, what we do is we have our DFA and we reverse our transitions to get an NFA, and then we convert that NFA back to the DFA, and then that will help us in minimizing the DFA. And this is actually very simple and elegant. Okay. Even in this case, we have exponential worst case. We have exponential worst case complexity. Worst case complexity. That's exponential. So that's a bad thing for it. But still, it is simple and elegant. Okay. And this guy, Hopcroft's algorithm, actually has the best worst case complexity. So it has worst case running time analysis, the best. And that is actually big O of ns of log n, where n is the number of states and s is the size of the alphabet. Okay, the size of alphabet, whatever the input alphabet is, what is the size of that, and n is the number of states, and it has the best worst case running time analysis. And one more thing in the Brzezinski is it can be used for DFAs, minimizing DFAs, as well as NFAs. That is added advantage. It is simple and elegant, even though it looks it has an exponential worst case complexity, but still practically speaking it's much better algorithm than others. Okay. Now in this lecture we actually take up the Moore's algorithm. It's also called the table filling algorithm, to minimize our DFA. Now table filling algorithm actually recursively constructs the set of distinguishable pair of states. Okay, when all distinguishable state pairs have been identified, any remaining pairs of states must be then equivalent. All right, such states can be merged. They're minimizing the automata. I mean, we firstly see the distinguishable states, and then if we see some states which are not distinguishable, that means they are indistinguishable, they are equivalent, and they can be merged. Right. So we have some bases for this. So what is our basis? Actually to see how we can say some states are actually distinguishable. So we say some if we have some two states, say for example P and Q, or any state, two states which belong to the Q, and we say if P belongs to the F, so P is actually a final state and Q is not a final state. So we are talking about two states out of which one is a final state, another is not a final state, or vice versa. I mean, we can say that P does not belong to F and Q belongs to F. So if this is a scenario, one is a final state, another is not a final state. Either P is final state or Q is not a final state, or P is not a final state and Q is a final state. Then we say that P and Q, these two states P and Q, are actually distinguishable pair of states. So they are distinguishable because we're gonna find these distinguishable pairs. Okay, writing full distinguishable pair of states. Okay, and then after having the basis, we can go the induction. We can use the induction to find out other distinguishable pairs. So what is the induction saying is, if we have the states, say for example P, Q, R and S, we got 4 states. They all belong to the set of states we have, that is Q, and our input alphabet A should belong to the sigma, that is our input should belong to the alphabet we have. It should not be beyond that. We know that, that's simple. And then we say if, say for example R comma S equals to, what it say is that we use a transition from state P on A, okay, and we have a transition from Q on state A. If we say this thing, what we're saying is, if you do a transition from the state P on an input sim A, and you reach to the state R, and from Q on A you reach to state S, and if we have previously seen that R and S are distinguishable, say maybe because of this thing, where we say that P was a final state and Q was not a final state, so they are distinguishable. And if R and S was already distinguishable, and we saw that from P and Q, on taking an input A, we have gone to these states which were considered to be distinguishable, then we will say that this state P and Q are also distinguishable. So if R and S was distinguishable, then P and Q is also distinguishable. So we will use the basis and the induction and try to see which states are distinguishable, and at the end we will see some states which are not distinguishable. Actually, then those states are equivalent and we'll merge them, right? These things will be more clear when we take up the example. Let us take an example. Let me change my, okay. Right, we have a DFA with an input symbol of A comma B, and we got the state Q equals to, say for example 0, 1, 2, 3, 4 and 5, and final state is, say for example 2, 3. Now let me draw my diagram. So this is my state 0, which is the initial state. Okay, let me draw it. Now this is my DFA, wherein I have the couple of final states 2 and 3 are my final states, and I could have also here some dead states and unreachable states. If there are, for example, maybe I have a state in this also like this. One of the state is like this, say state 6, which goes like this. So this is something which is a unreachable state, or there may be some dead states. Okay, we got to remove them first. So I am in this diagram, we don't have the dead states or unreachable states now anymore. So we talk about the pure algorithm, and the first step, say for example we have done it using depth first search or breadth first search. We have removed the dead states or unreachable states, and now we are on a pure DFA, and we want to minimize the equivalent states, right? I mean, we want to merge the equivalent states. So in table filling algorithm, we actually have a table which is a matrix, because we have 0, 1, 2, 3, 4, 5. So it will be 5 cross 5 table. So it will be like this. So it will be a 5 cross 5 table, right? So where we have, say for example, this is my 0, 1, 2, 3, 4. Actually I had 6. Okay, let it be here 5. So 0, 1, 2, 3, 4 and 5, right? One more on this side, not a problem at all. Now the thing is that we want to firstly do a more efficient way of doing things, because in this we have a lot of things which we don't need, because we want to find which states are distinguishable, right? And if you see 0, 0, this guy, this is same 0, 0. So we're talking about the 0 state. So 0 state cannot be distinguishable from itself. So it's not a word to take, right? So whatever 1, 1, it is again the same thing. What about 2, 2, 3, 3, 4, 4? 5 5. So we should not take the diagonal at all, right? And what about this 0? Then we have this state. This is say for example 0 1, right? And what about here? What about this state? This is, we're talking about this state 0 1. So we are actually talking about the same. So if we are done with this, so we should not take this because this is already done here. Same is with the 0 2, or in this case that is this guy and this guy. Similarly this guy, this is 1 2, and 1 2 is here. So that means we should take only half of this triangle, right, below the diagonal, or maybe above the diagonal, whatever you like. But above the diagonal, if we take, that is redundant, because if we have done with the states 2 1, that is same as here 1 2. So if we are done with the 2 1, this guy, I should not be worried about this guy. So what I do is I don't take this half of the triangle, I take only the bottom half, right? And the better way is to draw a table like this. Now if we look at this, in this case the first box is now to be taken, right? The first box, this guy, let me change the pen to highlight the things properly. Let me make it yellow. Okay, this guy I'm talking about 0 0, it is not to be taken, right? Because we're talking the same state, and going in the diagonal this way up to this way, right? I don't have to take any of these guys. So how I make an efficient table is, we will first construct the table in the order of the states. For example, if we have a numerical order or alphabetical order, we order them, okay, and then list all the states except the last one in ascending order, okay, along the top. So we say, for example, here, so on the top we say, since it's a numerical, so we say 0 1 2 3 and 4 on the top, except the last one 5. I skip it. So on the top I go in the ascending order, and then on this side, okay, on the vertical side, so on this side I will do this, that I will say, I will start from I will do it descending order, 5 4 3 2 1 and 0. I skip. The first one is skipped from this side, and the last one is skipped from this side, right? So I have a table now, okay. This is my table. Now the first row will be full, because we say 5 with the state 0, 5 with the state 1, 5 with the state 2, 5 with the state 3, and 5 with the state 4. 5 5 is not there. Now similarly 4, but I don't want to have 4 4, right? So 4 will be up to this only, 3 only. So 3 will be up to 2 only, because I don't want a 3 3, because 3 cannot be distinguishable from the 3, so cut it off. Then 2, and 2 will be up to the 1, and then the 1, right? So this will be our final table, so I don't have to worry about the upper triangle or lower triangle or whatever, right? So I will do this way. So what I did, on the top, whatever states we have in the ascending order, and skip the last one, and in the vertical here, rows, go from the descending order, starting from the last state, that is 5 4 3 2 1, and skip the first state. Then draw your rows and columns, right? Now we have to find the distinguishable states. How we do that is we use first our basis. Now what is our basis for the Moore's or table fitting algorithm is that if one state is final and other state is not final, they are distinguishable, right? So if we say we have, and if you look at in the top, we have 2 and 3 is our final state, right? We have 2 and 3 final. So anything 2 versus all non-final states or 3 versus all non-final states have to be marked. So what I'm saying is we got 2 and we got 3. So if we talk about this cell, this is 2 5. So this 2 is a final state. So 2 is a if I put a star here, 2 is a final state, 3 is a final state. So 3 is a final state, 2 is a final state. So we're going to talk about this cell. This is 2 5, so cross it. So this is distinguishable. 3 5, cross it, because 3 is a final, 5 is not a final, because one state need to be final, another state not to be final. That is our basis. If you forgot, I will show you my basis, which I said here, that one of the state is final, other is not final, or this is final, that is not final. So we say they are distinguishable, right? So that's what I'm applying here. Similarly, 2 4 and 3 4, or we say 4 2 or 4 3. Now what about this? This is 3 2, because 3 is final, 2 is final. I'm not talking about this guy. That's not my basis. And what about this guy now? 3 0, one final, another non-final, cross it. One final, the non-final, cross it. What about this? No, I can't. What about this? 2 and 0, yes, one final, another not final. So this is table filling basis. And we have 2 1, yes, we can do that. And that's it. So we have the first iteration wherein we use the basis, and we see which is one state is final and that is not final, and we say they are distinguishable. Okay, so these other states are potentially indistinguishable, then we can merge them together, but we have to further investigate using the induction. Okay, now we'll use the induction and try to see out of these which guys are distinguishable, and if anything is left out, then we can merge that. Let's first try to write which states are left out, right? So starting from this state, excuse me, so we say we have firstly this state. What is that? This is 0 1, so we write here 0 comma 1. This is my one of the states here. Then we got also the 0 4, and we got the 0 5, right? 0 1 0 4 and 0 5, right? Now this one 1 4 and 1 5. Then we have 1 4 and we have 1 5. Then about this is 2 3. Then we got 2 3, and then we got in fact this one is the last one. This is a 4 5. Okay, now we try to use induction and try to see whether they are distinguishable or not. There's another pen. So what about the 0 1? Let's take about the 0 1 first. Okay, if we discuss it here on the downside, we say I'm talking about 0 comma 1. So induction says that if I use a transition from 0 on input A, and also I take from 1, because I'm saying 0 1, a transition on input A, let me see where they will go on A. 0 on A goes to 1, and 1 on A goes to 2, so that means 1 2. So that means they are reaching to 1 comma 2. Now we have to see, is 1 2 distinguishable? If 1 2 is distinguishable, then 0 1 is distinguishable by induction. This is what we said in the induction, that if we have a transition and we say that if this is distinguishable already marked in the table, then 0 1 will also be marked. So let us see. Firstly, 1 2. This is the 1. Okay, now look here, this is the 1 and this is the 2. It is all already marked, right? If it is marked, that means 1 2 is distinguishable. That means 0 1 is also distinguishable. So what you're gonna do is you have to cross it here as well. So I'm gonna cross it here as well, so because this is distinguishable now. So what I do is I will cross it out because I have done with this thing. So for 0 4, now I will try to do with the same thing with the 0 4. 0 comma 4. So what I'm gonna do is I will try to see a 0 on A, where it will go, and 4 on A, where it will go. So let me see 0 and 4 on A. 0 on A will go to the 1, and 4 on A go to the 5. So that is 1 5. So what will come up here is 1 comma 5. Is it? It is, I don't know what's happening with the pen. 1 comma 5. So now I have to see about the 1 5, that is here. If you look at it 1 5, it's not marked, so we can't just say that this is not distinguishable, because maybe later on it will be come out distinguishable. So at this moment I can't say anything about it. Okay, so what I do is I have 1 5 here, right, because I have not worked out 1 5 yet. So I will do what? I will keep this 0 4 under the 1 5, right, because when I work the 1 5, because look what we are saying is, if 1 5 is distinguishable, then our 0 4 is going to be distinguishable, right? If 1 5 is distinguishable, 0 4 is going to be distinguishable, but 1 5 is not worked. If on working further I see that 1 5 is not distinguishable, then 0 4 will also be not distinguishable, but maybe it will come up it is distinguishable, then 0 4 will be distinguishable by induction. So therefore I have not yet worked 1 5. I will keep it this 0 4 under this 1 5, right, and I'm finished with this because I have kept it here. So the is 0 4 distinguishable or not, it will be decided when we work on 1 5 later on, right? This is 5. So we take up now the next guy, that is the 0 5. In fact, we can work on other input for this, because if I couldn't decide on the A, maybe I will decide on the B. So what I do is I will try to chuck out the same thing on B. Okay, let me try to see where 4 goes from B and where the 0 goes from B. So if we see here, for 0 on a B goes to 4, and 4 on B goes to itself, so it is 4 4. So it is 4 4, right? Now 4 4 is the same state. So when it's the same state, we don't have any info about the same states here, because we have 4 and 4. It is this thing which is having no info, so I can't say anything about it. So that's why I have kept it under the 1 5. So the fate of the 0 4 will be decided when we take up the 1 5. Now we can cancel out the 0 4. Similarly, we go to the next state, that is 0 5 now. And we take up here the 0 5. So what I say on 0 on A, comma, delta 5 on A, where it will go. Definitely 0 goes to the 1, we have seen that. We have to see 5, where 5 goes on A. 5 on A goes to 5 itself. Is it? 5 on A goes to 5 itself. So it will go to the 5 itself. Now what about 1 5? If 1 5 is already distinguishable, then I can say 0 5 distinguishable. Let me see 1 5 by induction. So here it is 1 5. In fact, it is again the same story, because 1 5 we have not worked yet 1 5, so it is again going to the 1 5. So what I will do is either I will do one thing, I will try to see the B state. Let me try the B on it, because I didn't got the info from the A. Let me go to the B of 0 on A on B, and delta 5 on B, where it is gonna go. Okay, because 0 on B will go to the 4, I know it, and 5 on B, 5 on B go to the itself 5, so it is the 4 5, right? Is it 4 5 or 4 4? This is the problem, because here we have 2 transitions on B. This is not here. It's A only. 5 on B goes to 4. Okay, so 5 on B goes to 4. 4 4, that is the same state, that's no info. 1 5 not yet done. So what we do is we keep 0 5 under the 1 5 here, right? So so 1 5 is also here. So when we complete the 1 5, sorry, it is 0 5, right? So we keep 0 5 under the 1 5, so that when we finish the 1 5, we will decide what 0 4 and 0 5 gonna be. Okay, and in the states here. We will cancel the 0 5. We had done with 0 5. Now what about 1 4? Okay, so we'll do same thing with the 1 4. Now let me pause a bit. So we are saying on 1 4, that means on 1 on A and 4 on A. Where have they gone? 1 on A here, 1 on A has gone to the 2, okay, and 4 on A has gone to the 5. That's 2 5. Now let us see from the table 2 5, is it marked or not? 2 5 is marked. So if 2 5 is marked, 1 4 should also be marked by induction. So 1 4 need to be marked. So we will mark here this guy as marked by induction. Okay, so we are done with the 1 4. Now comes the story with the 1 5. Now we try to see 1 on A and 5 on A goes to we say 2 5 to see 1 on 5. 1 on A goes to 2 and 5 on A go to 5 itself, so it goes to the 2 5. Okay, so if 2 5 is distinguishable, then 1 5 is distinguishable by induction. So let us see here 2 5. 2 5 is already done, already marked. So if 2 5 is marked, then 1 5 will be marked, right? So 1 5 is going to be marked, so this guy is to be marked. Okay, now if 2 5 is 1 5 is marked, that means 1 is distinguishable, then 0 4 will also be distinguishable, because now we come to this here, that 1 5 is marked, so 0 5 should be marked. If 1 is distinguishable here, okay, then where I'm talking about, then 0 4 also need to be marked. So 0 4 plus 0 5, which were under this 1 5, should also be marked. So 0 4 0 5, they gotta be marked, right? So this will be our stuff now. So we are done with all now. 1 5. Now same thing is to be done with the 2 3 and 4 5. So we are trying to do the same with the 2 3 state. 2 on A and 3 on A, they go to the 2 2 state. If you see here, 2 on A goes to 2 and 3 on A goes to 2. That is 2 2 state. That's the same state. So same state in our table has got no info. Okay, so 2 on 2 is here, that's no info. And same with the 2 on B, so we check with the B, and 3 on B, that goes to 2 3 state. Okay, and that's the same state, 2 3. So it is no point that we put 2 3 under 2 3. So no point. So we conclude that we have no information. We can't say that 2 3 is distinguishable. Same is with the 4 5. 4 on A, 5 on A goes to 5 5, the same state. And we check for the B. 4 on B and 5 on B goes to 4 4. So 4 and 5, if you say 4 on B goes to the 4, 5 on B goes to the 4, that is the same state. Okay, 4 4. So again, our table has no info for that. So we conclude that we can't say that they are distinguishable, and this will be our final table now. And we see that 2 cells are not marked, so we can't say they are distinguishable. So if we can't say they are distinguishable, they are indistinguishable, or in other words, they are equivalent. So we can merge state 4 5 4 this state and this state together, right? So the 2 and 3 and 4 and 5, so we can merge these states together, 4 with the 5. So 4 is equivalent to 5 and 2 is equivalent to the 3. Okay, so our final DFA will be look like something. So 2 and 3, they got to be merged. Okay, so when we merge them, we keep only one state. So that means whatever inputs here and here we have to do it with the both of these now. Similarly 4 5, they are equivalent, so we got to combine them. So 4 is similar to 5, 2 is similar to 3. Okay, so now we got to combine 4 5, so these two will be combined, these two will be combined to get our final DFA. So it will be kind of like this. Now this is our final minimized DFA. Okay, I combine 2 3 and I combine 4 5, as you see here, the original one, 2 3 and 4 5. So this was our 2 and 3, both of them were final states. So we make 2 3 combined as a final state. Okay, Now 2 had an A and B coming to itself, so this is what's happening here, A and B coming to itself. 3 has an A and B coming to itself, so 3 also has an A and B coming to itself. And 1 on A goes to 2 and on B goes to 3, so we say on 1 on A and B go to this state. Okay, and similarly we combine 4 5, and 4 5 are here, and 4 on A goes to the 5. That's the 5. 5 is in of itself, so it goes to itself. 5 on A goes to itself. Okay, so 5 on A also goes to itself. So 5 on B goes to 4, and 4 on B goes to 4. So 4 on B goes to 4, 5 on B goes to 4, because it's now the single state. Now by this we see we have here 1 2 3 4 states, and here we had 1 2 3 4 5 6 states. And even though there were states and non-reachable states, so they all will be minimized. So it's a huge gain. It will be faster, and the important thing is it should not accept some different language. It should accept the same language. The language accepted by this guy should be the same the language accepted by this guy. So this is our table filling algorithm, and that's all for this. You can try up your hands on more examples and you will be fine. So until next time, ma salama.